Is it all right? Brilliant.
Yep.
Fantastic. We've got it. Okay, it's great to be here, and I hope you've all had an enjoyable day. And I know it's been quite a lot of information. So hopefully this last talk will be something a bit interesting for you. Lecture I would like to give, it aims to give you a taster of the kind of material that we cover in our first and second year courses looking at past environmental change. And I'm also going to use an example from some of my own research, which centers on volcanic ash and environmental change. So you can get a glimpse of the kind of things, some of the scientific work that students in Cambridge Geography can get involved with. So in the next 40 minutes, I'm hoping to convince you not just of the importance of studying the past climate to provide analogues for the present and future climate change, but also that understanding the precise timing of past environmental change is essential to deciphering the mechanisms driving Earth's climate. So let's see. So my lecture is going to be in 3 parts. First, I want to introduce you to paleoclimate studies, how and why we study past climates to understand past, present and future Earth system processes. And then I want to introduce you to my own area of research using volcanic ash, something called Tephra, so Tephra chronology. And then the main part of the lecture will be an example of how we use ash layers or Tephra layers to compare climate records from different locations with near annual precision so that we can track the propagation of climatic changes through space and time. Okay, so strap in. So I think we all know that our Earth's climate is changing. It's not really controversial anymore. And predictions are, of course, that warming will continue and we will potentially be pushing the Earth outside of its current boundaries into irreversible changes. We know from records of past climate and geological records that Earth's climate has always been changing, but the current rate and degree of warming is certainly unprecedented during the last 11,000 years, so the Holocene, our current interglacial. Now, when we want to study future climate, we make predictions using climate model simulations. Now, climate models vary in their complexity. There's a lovely quote here by George Box about models, not just climate models, but all models are wrong, some are useful. And we need to think when we're using climate models about the uncertainties within them. Most of the complex ocean atmosphere coupled global climate models, don't worry about that too much. They use measurable and quantifiable parameters, so physical parameters such as temperature, pressure, controls and evaporation, condensation, the degree of reflectance or absorbance of radiation by different surfaces, etc., to predict the behavior and interaction of different parts of the Earth's climate system. They're based on physics. But all of them include simplifications because we only have so much computing power. We don't necessarily understand every part of the system. So we have to make assumptions that allow our models to test specific relationships or parameters. So we might have compromises such as compromises based on spatial resolution, working at different grid cell sizes, or we might have compromises by simplifying some element of the climate system that we're not so interested in studying. So despite the uncertainties in models, as you know, and you will have seen, I'm sure from IPCC reports and similar, that whilst there are variations in the predictions of climate models looking forward, and you can see some of them here in this image from the one of the older IPCC reports, the predictions all vary, but they all show agreement that the climate is warming. Now, it's really important for us to know which of these predictions is closest to the truth or what is likely to happen, and to understand why it is that one particular model works. So the information about the past climate provides the perfect test case scenario for us to hindcast our climate models, so to run them for periods of time in the past and see which of our simulations are best able to replicate known climate scenarios. Additionally, by using real evidence of past environmental processes, we can reveal connections and mechanisms between parts of the climate system that are beyond our modeled resolution, whether that's spatial resolution or resolution in terms of time, the spacing of events that it's reconstructing. So of course we can use instrumental measurements. This diagram shows the kind of time period and the different records we can use to tell us about past climate. So we're starting at 2000 the year 2000 here, moving backwards in time. And we've got things like satellites, radiosones, pilot balloons. We've got direct sampling of the climate in different ways, going back to 100, maybe 200 years, even earlier than sort of 1800. We've got instrumental series and ship logbooks. There are things like people's personal accounts and historical documents that record past climate in different ways. But they only get us back a few hundred years. So if we want to understand and test our models over longer periods, maybe thousands of years or tens of thousands of years, we need to find another way to reconstruct the climate from the past. And that's where geological archives or biological archives, such as tree rings, ice cores, lake sediment records, stalagmites, stalactites, and other types of archive really come into their own. So we can use these natural archives, geological archives, to reconstruct past climate. And all of them work in different ways, and I'm not going to go into all of those right now, but I'm just going to give 3 examples of paleoclimate archives because they'll come up later in the case study I'm going to show. So one of the most fantastic archives that tell us about past climate are the ice cores that have been collected from on top of the ice sheets or in locations on ice sheets and glaciers around the world. These are really fantastic because they're actually meteorological records. The material accumulating, the snow being compressed into ice, comes directly from precipitation. So it's a real sample of past meteorological conditions. That means that we can tell things quite straightforward inferences. Thick layers, more snow, more precipitation. Thin layers, less snow. There are things that we can measure quite easily, but there are also chemical traces we can measure that tell us, that sample the atmosphere. We can find evidence for material deposited on the ice, like dust or volcanic ash, other aerosols, and we can find also measure the ice itself directly for its composition, and again that samples the atmosphere one way or another. That means that we can collect different kinds of signals from on top of our ice sheet and reconstruct how those things have varied through time. How has precipitation varied through time? How has dust deposition varied through time? And we can put a time series on that if we can date the archive we're looking at. Now, in the case of ice cores, and there are situations, or there are some ice cores that preserve annual layers because snow falls annually. Up on the Greenland ice sheet, for example, there's not a lot of snow in winter, it's too dry. So we get the spring and summer snowfall when there's moisture available, and we can see those layers preserved within the ice cores. So in some cases, we can count the years in our ice cores, just like we would rings in a tree. Now, another really fantastic type of archive is what we call speleothems. These are stalagmites and stalactites, so limestone or calcium carbonate materials forming within caverns or holes or caves within limestone landscapes. These form by the dripping of water through the soils, through the geology into the cave, so it's a groundwater fed system, and as that water enters the cave void, there's a decompression which causes it to precipitate calcium carbonate. And so you can see some speleothems like this one in the picture seem to form in layers. They're not perfectly annual layers, but you can measure changes in time in the composition of the groundwater. It might tell you something about the land cover that the water has passed through, and will tell you something about precipitation, as well as sampling chemistry of the atmosphere. And again, we can date speleothems very well using an isotopic method. And again, we can plot different signals through time back through our speleothem records. And some of them grow for hundreds, if not thousands of years. Now, my favorite type of record to work with are lake sediments. Probably because the field work isn't quite so difficult as getting off onto an ice sheet or down into deep caves. I prefer my time on a boat. So I tend to study lake sediment records. So these are sediments accumulating at the floor of a lake over time, and they're accumulating material from the catchment. So there might be runoff material getting washed in with rainfall and runoff into the lake basin and settling out. There's fauna within the lake that might say fish, but also microfauna like algae and other flora like plants living within the lake that also eventually end up in that sediment record. We might get dust blown in, pollen blown in, and again, we've got precipitation and exchange with the atmosphere. So we can get a lot of different proxy signals, biological, chemical proxy signals through our lake sediment record. Now, in particular conditions where a lake, the water in a lake is well stratified and seasonal mixing doesn't disturb the sediments on the bottom of the lake, we have the potential in a lake to preserve annual layers in a similar way to ice cores or tree rings. So we could look at there are different types of annual layers in lakes. We call them varves. Clastic varves on the right here tend to form from the seasonal inwashing of material runoff, sediments from runoff. So maybe in a lake at the front of a glacier, we might get seasonal melting of the glacier washing material into the lake. And organic varves, which I'm going to focus on here, there's a picture of some organic varves. These form in a situation where we get seasonal winds causing upwelling of nutrients within the lake, and at different points within the season, different types of algae will form or will bloom, an algal bloom, and as they settle out, as they die, they form clear layers in the sediment. And you get these, you can see in this picture here, light, dark layers of algal blooms, and then the autumn, some organic material washed in, which are our dark layers. These are really special types of record because we can count those couplets of algal layers and organic material being washed in, and we can count the years in our lake and provide a timescale for our proxy records. Now, the wonderful thing about annual records, of course, is if we can count from one year to the next, we can record climate and environmental development beyond the resolution of any global climate model. And therefore, we can start to understand even the most smallest changes or the quickest changes and what impact climatic changes and what impact they've had on environments. Okay, hold in your mind the types of archives we can work with. And I'm just going to move across and talk a little bit about Tephra chronology before I move on to my case study. So I'm a Tephra chronologist, and that's one of my hats. And I'm sure you all have seen spectacular images of volcanic ash following explosive eruptions, either being blown up into the troposphere or into the stratosphere, transported over vast distances and blanketing landscapes. And these are all pictures from, oh no, they're not. The top one and the right one are pictures from the 2010 Eyjafjallajökull eruption in Iceland. And the bottom left is a picture from Montserrat of ash falling out of that volcanic plume onto a landscape. Now, everything that's explosively erupted, like volcanic ash, from a volcano, we call Tephra. So that's where this word Tephra comes from. It also incorporates blocks and bombs and bigger bits that are deposited, close to the volcano. They don't travel so far. And this Tephra, this ash that can travel a very long way. The ash fraction is very fine, and deposition begins immediately at the time of the eruption and is complete usually within days to maybe weeks after an eruption event. And wherever that ash falls out, it creates a layer which captures the moment in time of that eruption. So weeks, maybe days to weeks at the most, wherever we find that layer. So here's a schematic that might help to envisage that. We have a volcanic eruption, and we can get ash deposited by pyroclastic flows, which travel down the side and the slopes of the volcano. So we can get ash deposited falling out from a plume that is expanding in the troposphere or stratosphere, depending on how high it's been erupted. Ash can then fall out into all sorts of different systems. It falls out onto landscapes, but it's rapidly focused into places where sediments accumulate. So maybe within rivers, where it will be transported then out to oceans, within lake basins, where it can form very clear layers, and that's why I'm so interested in lake sediment records, but also within things like rock shelters. We can find ash layers within archaeological sequences in rock shelters as well. Now, naturally, a Tephra layer's thickness will decrease the further you move away from the volcano itself, and also the particle size of the shards of glass, the ash within that Tephra layer, will also decrease with distance as the largest particles fall out first, closest to the volcano. So near to a volcano, we might be looking at layers of ash that might be meters thick, maybe centimeters thick, and as we get further away, we start to find layers that might just be a few millimeters or a few centimeters in thickness. Now, at the furthest extent, sometimes thousands of kilometers from a volcano, we can still find volcanic ash within our sediment records, but the layers have become so thin and the particles so fine-grained that we can't see them with the naked eye. And we call these Cryptotafrail, so hidden tephra. Because we can't see them, we can only find them by processing the sediments in the laboratory. And underneath my office here is my Cryptotafrail laboratory, where we specialize in doing this here at Cambridge. And every year we have undergraduates working in the lab here on a project using Cryptotafrail. So it's part of the furniture in the department, I guess. So we carry out a process to extract and identify volcanic ash within sediment records. And if we find it, when we look down the microscope, it looks something like this. So each one of these circles here is a view down a microscope about half a millimeter across, let's say. So our particles, if we're lucky, are several hundred microns in size. And that's not very big. That's sort of a thickness of a human hair. And they might be clear like these top ones, or they might be browner like these ones. And how they look depends on the composition of the magma that they formed from and the eruptive processes themselves. Now, what's so interesting about Tephra is that these far travel deposits are made mostly of volcanic glass. Volcanic glass forms during the volcanic eruption as the magma is quenched very quickly, so it freezes very quickly. So it's what we call a supercooled liquid. You've probably seen medieval window glass or old window glasses that are thicker at the bottom than the top, because glass is a liquid. It actually flows very slowly over time. And because it forms fast, it doesn't, there is no time for crystals to form within these particles. So we can't, there's no time for the atoms to arrange themselves into any crystal structures. So it freezes as a liquid, and it preserves the composition of the magma of that volcano at the moment of the eruption. So we can use this as a kind of fingerprint. We can use the elemental composition of our volcanic glass as a fingerprint for an individual eruption event. So there's a diagram here that just shows a suite of composition of data sets where I've analyze each point as an analysis on a different volcanic glass from a set of different standards, different samples, sorry, each one in a different color. And you can see that each tephra, you get a cluster of compositions within the volcanic glass, and you could see the differences between them. So because we can identify a volcanic glass using its composition, we can match a volcanic deposit from one site to another site. And if we do that, we can start to trace the same volcanic ash layers between different kinds of archive and across vast distances. And this is really powerful because it gives us a moment in time within our ice cores, our lake sediment records, or maybe our volcanic sequences that we know is exactly the same moment in time, down to weeks or days. And that's very powerful when we want to date and correlate and compare climate signals between different kinds of archive. This map at the top shows some of the volcanic, some of the tephra deposits from volcanic eruptions over the last 2 million years that we've traced, or actually these are all within the last 100,000 years, sorry, that we've traced over intercontinental distances, so between more than one continent. So you might have heard of the Younger Toba Tuff. This was a huge eruption about 74,000 years ago from Indonesia, and we find the tephra. Actually now it's been found in South Africa most recently, so we find it right across the Indian Ocean into South and East Africa. We've got an eruption called the Mazama Ash, took place 7,000 years ago from Crater Lake, what's now Crater Lake in Oregon, and that we find that right up into the ice cores in Greenland. So some of these volcanic ash layers we can trace a really long way, and that means that we can compare what's happening in our paleoclimate records from, let's say, the South China Sea across to East Africa and up into India with the same moment in time. It's a very powerful technique. Okay. So just to visualize that in a kind of schematic, this is an ice core and a lake sediment record, and we might find the tephra layer here in our lake sediment record, here in our ice core, and according to our working chronology, that might be about the same moment in time, but actually with the tephra layer there, we can line them up incredibly precisely and be comparing what's happening in the climate in Greenland and in the environment around our lake sediment core, let's say a lake sediment core from Germany, or that's where this one's from, and we can line those up really precisely. Sometimes we're lucky, we can find visible tephra layers as well. And the one in the bottom right picture here, this sort of pinky grey band, is a visible tephra layer from another annually layered lake, from this one from East Africa. So this is a lake just close to Mount Kilimanjaro. And these are the kind of things we're finding, and these beautiful, unbiased, beautiful volcanic glass shards. Okay, so the idea of correlating different types of sedimentary record or geological record using volcanic ash leads us into my example of tracing climatic change in space and time. So in particular, looking at a climate change event during something called the Younger Dryas cold period. Okay, so now we're going to put our time traveler shoes on, and we're going to go back around 12,000 years. 12,000 years ago, the Earth experienced its last really cold stage. It's about a 1,000 year long interval. And this was almost, well, let's say 8,000 years after the last glacial maximum, which took place between sort of around 20,000 years ago. So this isn't huge ice sheets across the Earth, but this is the re-expansion, the re-advance of some of those waning ice sheets before we entered our current interglacial, the Holocene. So it's a last gasp of the last glaciation, I guess. So I'm going to take us back to 12,100 years ago. And here's a reconstruction of what of the landscape in the Younger Dryas. This is an artist impression of the landscape in the Younger Dryas. Actually, this is an artist impression of the Eastern Netherlands, but actually wouldn't have been so different from the area from East Anglia. So we're looking at sort of tundra type environments. We've got rivers refinding their pathways after the last glaciation. We've got vegetation starting to come back, but it's quite cold, so it's cold climate vegetation. And we've got quite bleak and open landscapes, ready to be reoccupied by vegetation and fauna as we move into the Holocene. Okay. In terms of, let's look at this diagram here. So this figure shows a few things. We've got here at the top, Dryas octopetala. This is actually the flower, and it's an alpine flower. And this is what the Younger Dryas is named after. So this was first recognized in lake sediment pollen sequences. So we can extract pollen from lake records and reconstruct the vegetation on the landscape. And the Younger Dryas is named after this because across Europe, we suddenly were finding this alpine flower, which indicating the cold climate conditions during the Younger Dryas. Top right here, you have a picture of the what we call the Loch Lomond re-advance. So that this small ice sheet, I mean, it's large for Scotland now, but it's smaller than the large ice sheets we would have had connecting up with Europe during the last glacial maximum. A re-advance of glaciers across the Scottish Highlands, maybe a small amount of ice in the Lake District, but that's about it for the Younger Dryas. What we would have had during the Younger Dryas, though, is the sea ice margin pushed further south with the polar front, probably around the latitude of around sort of 50 degrees north. So sea ice would have been much further south. The UK would have been bound up then in that sea ice most of the year around. And as we push the sea ice south, we end up with the trade winds moving along that polar margin. So we've got the polar front and these westerly winds pushed further south than where they are today, where we normally have the winds traveling further north up here. Now we have lots of records of Younger Dryas preserved in lake sediments, in ice cores. And one of the best records from Europe comes from a very special lake in Germany. And this is a picture of the lake down here. This is a lake called Meerfelder Maar. It's in the West Eifel region of Germany. You can see it. This is the lake. You can see it sort of in the western part of Germany here. And this lake has formed in a crater. So this is a volcanic region of Germany. I don't know how many people are aware that there is a volcanic region in Germany. Relatively young volcanism. I think this volcano formed around 30,000 years ago, and a lake formed within it after that. Now, this lake is special because the sediments within the lake have these annual layers, and you can see a picture here, a thin section, a microscopic image of those layers through a section of the lake sediments from Meerfelder Maar. They form in this lake because of those tall, steep crater walls they're very high, and they mean that the way the wind blows over the top, there's only one season really where the wind causes that upwelling you need to bring up nutrients, and otherwise it's a very sheltered lake, and it has anoxic sediments on the bottom. So we get these biogenic varves, these algal blooms are the light layers, and then organic sediment layers in between. So if we look at the situation in the Younger Dryas, the polar front would have been pushed further south for much of the Younger Dryas, and westerly winds in the early part of the Younger Dryas would have been ploughing over the North Atlantic into sort of northern Europe here, where Meerfeldermaar is. Now, because of this fantastic record, we wanted to look at the Younger Dryas in Meerfeldermaar in more detail to see what it could tell us about the onset of this cold period and what had happened within it. Now you can actually see the onset of the Younger Dryas marked off a change in this record from 1 year to the next in the Meerfeldermaar record, and this marks the beginning of the Younger Dryas. The graph that's overlain on the picture here shows the varve thickness, so the thickness of each of those annual layers, and you see really there's a change here, a very abrupt change here from thick varve layers to thinner varve layers, sorry, to thicker varve layers. Okay, we can look at that on a graph much more easily than we can on that little overlay. My colleague Akin Brouwer has been working at this lake and has measured lots of different properties in the lake sediment record over the years that tell us about the local environment conditions. So I've got two graphs up on the page here. They both are looking at the Younger Dryas section of the Meerfeldermaar record, and they're orientated in the way the sediment cores are taken. So we've got 11,400 years at the top here. So this is just into the start of the Holocene interglacial, or current interglacial. And then at the bottom, we've got 12,800 years. So just before the Younger Dryas starts. So time in this diagram is moving from the bottom up to the top of the page. And what we see quite clearly is a change in the volumes of inwash sediment in the catchment at the start of the Younger Dryas, and change in the varve thickness. And then there's some sort of change happening in the middle of the Younger Dryas. And again, at the end of the Younger Dryas appears to be quite abrupt as well. Now we can look at these sediments under the microscope and try to understand what those changes mean. So at this bottom image here, these are all photographs of thin sections made of the sediment from this core. This bottom one, so this is pre-Younger Dryas, this is the warmer climate before the Younger Dryas started. We see quite thick algal bloom, quite even layers between algal blooms and autumn, which take place in the spring, and autumn detritus. So this is leaf litter or other organic material washed in during the autumn. And the actual individual couplets are less than half a millimeter, so they're quite thin overall. But they're quite balanced between the organic and the algal material. So this is a warm and stable climate. It doesn't look like it changes too much during this pre-Younger Dryas period. When the Younger Dryas starts, however, we get a really rapid change to these thick algal blooms, and we lose this organic material. We still get a lot of sediment washed in, so we have slightly thicker inwash sediment layers, which you see in this graph, and we get thicker algal blooms, which suggests that there is an increase in windiness, driving nutrient upwelling, which causes those algal blooms. But we're losing that organic signal. There's less organic material in the catchment to be washed into this lakes. So this represents what we think are windy, cold, and quite unstable climatic conditions in the early Younger Dryas. Now there's this abrupt change taking place, seemingly again 1 year to the next in the middle of the Younger Dryas. And here we see a change to a completely different climate scenario, a different climate scenario. In terms of inwash sediment, we've suddenly got lots and lots of material washed in from the catchment, and we've got a decrease in overall annual layer thickness. So we're losing those diatom layers, we're losing the thick algal blooms, and we're now just getting layers comprised, which are thinner overall, but comprised mostly of inwash sediment. So we've got an open landscape, less vegetation pinning down the soils, a lot of inwashing of sediment, but not much else happening. It's a cold and it's a stable climate. We don't appear to have much wind during this time. So there's a change taking place. So what we think is happening during this time period, is that we're moving, if we focus on the Younger Dryas, we're moving from an early Younger Dryas dominated by windy, cold and unstable climates to a later part, which is still cold, but the climate is much more stable, and that windiness, that storminess is gone that was driving those algal blooms. And as I say, it seems to be taking place from one year to the next. Now, the work that I did on these records was looking for volcanic ash. That's what I like to do. And we found a volcanic ash layer, which we call the Veda ash. And this came from Katla in Iceland, traveled all the way over to Germany, deposited it in this lake. And I've marked out where it is there with a green line on the graphs. And you can see it also, its position in a thin section of the lake here. And what we saw was the volcanic ash is deposited exactly 12,140 years ago. And that is exactly 100 years, and we know that because we can count those valves, 100 years after this abrupt change in the middle of the Younger Dryas from these windy, unstable climate into this colder, stable climate. So we've got a change in the climate, and then exactly 100 years later, our volcanic ash is deposited. Okay, there's some pictures of the very ash shards of glass down here. I won't go on about it, I think it's beautiful. There's amazing, intricate patterns that we get in this glass. Now, this transition that we've got in the middle of the Younger Dryas is interesting because it suggests that something is happening very abruptly, or at least the lake is responding very abruptly to something in the climate changing. Because the lake responds seems to respond from one year to the next. Now, what we think is happening, this change in our lake represents a decrease in windiness. So what we think is happening in the early Younger Dryas, we have that extended sea ice margin down to the latitudes that Meervelder Maar sits at, which means the polar front and the westerly winds are ploughing in over Meervelder Maar. That causes all of our thick upwelling layers, our upwelling of nutrients and our diatom layers. And then at some point during the middle Younger Dryas, we get a resumption of ocean circulation, or a strengthening of ocean circulation, bringing warmer water back up into the northern part of the Atlantic and pushing back that polar front. So it recedes further north, the sea ice margin retreats further north, and those polar front and those westerlies move further north away from the latitudes that Meervelder Maar is lying at. Now, we also see this two-part Younger Dryas structure in other records, and so we wanted to see if we could use our Veda ash marker layer to try to explore the relative timing of this event or this response in different sites. Okay, this diagram here on the top left, this map, the big pink blob, shows approximately the area within which the Veda ash has been found, either as a visible Tephra layer up in the sort of very northern part of the record of Europe, or as a Cryptotafrail layer, a non-visible ash layer right down into northern Italy. And the locations I've marked with a star are sites where people have also observed some kind of bipartite or two-part Younger Dryas, so a two-part climate within the Younger Dryas. So I want to take you next to a site called Krognes, which is in Western Norway up here. And here's a picture of the site, amazing cross-shaped lake up on the coast of Western Norway. And in Krognes, they also find the Veda ash from Katla. And let's see what their signal shows. So this, I'll just talk you through this diagram. This diagram shows time going from 13,000 years, so pre-Younger Dryas on the right through to, again, the start of the Holocene on the left. So time is moving in this diagram from right to left. And this is the record of in-washed sediment from Krognes. And that's the grey line. Don't worry about that green line, this wiggly green line. This grey line with a red mean trend through it shows the amounts of in-wash sediment in Krognes. And what you see, notice that the more is at the bottom, the axis isn't the way you'd expect. More at the bottom, less at the top. And what we see there, again, is there's an abrupt shift in the middle of the Younger Dryas. In this case, from a situation where we've got fairly stable climates with not too much runoff coming into the lake, probably frozen lake for part of the year, stable frozen grounds, not a lot of material in this catchment being washed into the lake, and then suddenly switching to a system where we get much less stable climate with lots of inwashing of sediment into Krognes up here. Sort of the opposite to what we see at Meervelder Maar then. And what we think is happening at this site, or what the authors who've studied Krognes think is happening, is that this is because the sea ice margin for Krognes moves in the early part of the Younger Dryas, the sea ice margin is way south of Crookness. So it's dry, it's a stable, cold Arctic climate. And then in the latter part of the Younger Dryas, as that sea ice margin retreated north, the westerly winds are heading straight for this site. So they get the west, at this site, we get the westerlies and unstable climates in the latter part of the Younger Dryas. Okay, and as I said, we find the Veda ash in this site. And in this case, we know that the Veda ash occurs about 20 years before the abrupt change. So if we line our two records up using the Veda ash here, you can see that we get a change in Meerfelder Mar, an abrupt change in Meerfelder Mar from windy, unstable conditions. 100 years later, we get the deposition of the Veda ash in both sites. That's some synchronous deposition. And then 20 years later, we see the polar front moving up, reaching the Crookness area. So there's a 120 years then between the shifting of the polar front away from Meerfelder Mar until it stabilizes itself or reaches the latitudes of Norway. So our retreat of the polar front took at least 120 years. Now we don't know when it began because perhaps it started further south than Meerfelder Mar. So other ways that we could test this idea, it's fine for us to say that it retreated like this. We've only got two dots to join up on the map. So it's been interesting since we did this work to see what other evidence has come from other types of record. We found that we have both the Veda ash and records of the Younger Dryas in the Greenland ice cores. And I also want to briefly look at a cave site in the western part of the Pyrenees called Seso Cave, which also records a bipartite Younger Dryas. So just coming to the end here, and I want to show you some work that's happened subsequent to the study that we published. And this is a study called by Bartolomeo Tal in 2015 from Seso Cave. And this diagram shows what's happening in the Younger Dryas in Greenland. And now time, sorry guys, is moving from the left to the right, 13,000 years ago through the Younger Dryas towards the Holocene. So as we move through the Younger Dryas, climate appears to be stable in Greenland the whole time. We see the Veda ash arrive, but there's no real shift in the climate, probably because the Greenland ice sheet is always in the Arctic. It's always north of the polar front. So there's no real change taking place within the Younger Dryas itself. Now at Seso Cave, the stalagmite record, which is further south than our Meerfelder Mar record, we see as the Younger Dryas begins very stable climates and some sort of shift taking place around 12,500 years ago. So we're seeing a climatic transition in Seso Cave, which is receiving its moisture from the North Atlantic, taking place before the transition we see in Meerfelder Mar. And their idea is that this transition represents the change, the reinvigoration of Atlantic circulation as the Younger Dryas climate starts to recover. And that would have triggered the movement of the polar front that we later trace through our records. Okay, so what does this study show us and what does it tell us about how the climate behaves? What we see in the past then, when we've got the precision of a layer and records where we can count individual years, is that climate changes, even when they're abrupt, might have very different local responses, and that those local responses might be lagged. So when we see a climatic change in one area, it might be a precursor of something we could see later on in another location. We shouldn't expect climatic changes to be felt exactly the same way everywhere at the same time. We see that there's some sort of this lagged response appears to be something to do with the behavior of the atmosphere, but intricately linked to the behavior of the ocean as well. Now we can only detect this 120-year offset because we've got high precision dating using our Tephra layer. And I think importantly, it sets up a challenge for our climate models to be able to resolve how the climate is behaving on annual to decadal scales in the past. And that's going to be really critical for understanding the way that future climatic change will unravel in space and in time as we move forwards. Okay, I'll leave it there. I've talked a little while. I hope that's okay. I hope it was interesting. I'm excited to hear your questions. So I'm just going to stop sharing my screen.
Thanks for that, Christine. That was very good. I mean, I always say this, but as a historian, well, I don't encounter things like that a lot. So, I enjoyed it, which is, I think, always a good sign. Hopefully the geographers enjoyed it. So we've got a question from Jack, which goes, I think, right back to the start of your talk, which is, what methods do you use to date speleothems?
Yeah, so typically we use a method called uranium thorium dating. So it's a method that uses part of the uranium decay chain. So this is the same, the decay of uranium is, we know the half-life of the decay of different parts of the decay chain. So from one unstable isotope to the next. And we can use different parts of the decay chain to measure time on different time scales. So actually we can use bits of it to measure the whole of geological time. For the last few 100,000 years, we use uranium thorium. So it's the rate of decay of uranium into thorium, which we can use to date anything made of calcium carbonate, because that precipitates uranium when the calcium carbonate is formed.
So someone asks, because volcanoes do not erupt annually, they are an irregular event, how do you know when it has erupted and which volcano is erupting?
Okay, yeah, so when we find a Tephra, if I find a Tephra layer, first thing I want to know is, where has it come from? When did it happen? Right, those are my challenges. So where did it come from? We can find out using its geochemical composition. So whilst I say every Tephra layer has a unique kind of chemical fingerprint, actually each volcano, let's say, has a kind of chemical fingerprint, and there might be each eruption might vary within a certain range that volcano or that volcanic system has. So we can use the chemistry to help us to identify the volcanic source, usually with some information. If we're looking in Germany, I know that my options are most likely to be Iceland, the Massif Central in France, maybe if we're lucky, something from Italy, maybe something from the Azores. That's probably where we're looking for. So we have a suite of places to start looking. And then we go to published data sets of volcano, of the composition of different volcanic deposits. So we have big databases of Tephra compositions that have been accumulated and put together over the years. So if we can then say, okay, I know my ash comes from this volcano in Iceland, and I know it's this eruption in Iceland, how do I date that eruption? We can directly date volcanic ash using another dating method, which uses the decay of potassium and argon, if we've got the right crystals. But also sometimes we can date our layers independently. So if we find a Tephra layer, let's say within a late sediment sequence, if we can date, if we've got radiocarbon dating or something else, some other method to date the sequence that ash is within, we might be able to date it by proxy. It's usually less precise than the dating directly on the crystals, but to do that, we need to be able to correlate back to a volcano, find the right crystals in the big outcrops and date those. So there's a couple of options. Yeah.
Interesting. And then just possibly preempting a question, we're talking about some quite advanced chemistry here, but I assume that for some, would this in theory be searchable by someone with no background in chemistry? So is it just sort of like an easy to use database, or do you have to also be up to speed on your volcanic chemistry?
I think you need to know the basics. You'd need to understand the range of compositions that we can receive. But remember, I think I said what my A-levels were earlier on. I did do geology A-level, but beyond that, it was English literature and ancient history. You don't need to be sort of a qualified chemist to do this work. We have lots of students who get involved with this kind of research, who come from varied types of A-level backgrounds. And you can sort of take the geochemical part of the work as far, or as, you can treat it quite simply, or you can go quite a long way with it, depending on your interests. But no, it's completely accessible, and it's within the abilities of all of our geographers.
Yeah. What about your historians? No, I'm joking. So Shreya asks, will Tephra layers in every single lake match up? I assume within a sort of a geographic region, will they all match?
Do you mean I don't know quite what. So let's say we're looking at 2 lakes in Germany. In fact, I've been studying another lake in Germany as well over the same time period. And we do find the Vedder ash in both lakes. There's another layer called the Lachese Tephra, which comes from Germany, actually, one of the last big eruptions from the Eifel region. We find that in both of our lakes. Chemistry is the same for those layers everywhere we find them. And then there are some other horizons that we find in both of them. And then there are some volcanic ash layers that are only in one site and not the other site. And that might just be to do with the pathway that the ash travels before it fell out. But the composition of the Tephra layer will be the same almost wherever we find it. Yeah.
Someone asks, how can we use algae in organic varves be used to monitor past climate change?
It's a good question. I didn't talk too much about that, but each type of algae, so there's lots of different types of diatom, let's say, which are really simple siliceous algae, like blue-green algae that clogs up the waterways. They form under certain conditions. So you know that they form under, particularly if you've got a lot of nutrients, under certain temperature conditions. Some of them are only like certain freshwater or saline conditions. So if we know the conditions a particular algae live in or bloom in, when we find those particular algae in the past, we use our information about their modern environmental settings to infer the environmental setting for the past. So if we know that you need to have temperatures or summer temperatures greater than 7 degrees or something for a certain algae to exist, then we know that that's the conditions in the past if we find it. So we use the theory of uniformitarianism, which is a nice long word, the idea that the present is the key to the past. So certainly within the last few 100,000 years, where we've got good similar boundary conditions to today, we can use modern relationships to infer what was happening in the past.
Lucy asks, when you go to one of these research sites, do you hope with an educated guess that a specific Tephra layer will be within the samples you take, or do you know of its presence beforehand?
Usually it's an educated guess. Yeah, I mean, very rarely do I do a study where I already know the answer. It would be nice. But sometimes we revisit a site. So somebody might have studied one thing and then we go back and take more cores and then we might know what we're expecting. But usually it's an educated guess. So for the Meerveldemar project, my colleague Akin Brouwer had been working at that site for a decade. It took me a few years to convince him to let me look for the bed of ash. He said, it's not there, we can't see it, it's not there. I was like, I think it is. So after a few years of discussion at various conferences, he said, all right, I'll give you a little bit of mud, Christine, you find it. And we did manage to find it. And actually we found a lot of other ash layers in that lake as well, which I haven't talked about today. So it's, yeah, we usually have an idea. I thought it would be there because we found it in northern Italy, we found it in Switzerland, so we know that it's in Europe, and it just takes a bit of convincing sometimes to let people get your hands on their mud. Yeah.
And then inspired by your talk, I think we've got 3 or 4 questions about, are you able to do Tephra chronology as part of your geography degree?
Yeah, very much so. So we don't have a long course on it as part of our undergraduate degree, but it comes up in our first year topics on environmental change in the Quaternary. So that's the last 2.5 million years. And then in the second year, I run another Quaternary paper, and it comes up in there as well. But like I say, at least once a year, at least one student per year does a dissertation project based on it. So I have a student who just finished collecting all her data. She's in her final year now, who's been working on short sediment records from Norway, which are about the longest one is 1,000 years, and we've been trying to build a chronology for those. And she's also been looking at pollen, looking at vegetation change over the time period she's doing. So her Tephra layers are providing a chronology or a time scale for her study of landscape change at those sites. So it's combining different methods.
Jack asks, what Tephra chronology studies are you doing at the minute?
Well, apart from that one in Norway that my student is doing, at the moment, I am working a lot in Eastern Africa on lake sediment records, where we're trying to understand tropical climate dynamics, but also working a little bit with studies of human evolution. So we published a paper a little bit earlier this year, which refined or pushed back the age of the earliest modern human fossils in Ethiopia, which are dated because of their relation, where they're found, they have volcanic ash layers above and below them. We managed to find the source of one of these volcanic ash layers that had never been traced before, and then carry out some high precision dating, and we've pushed back the age of our earliest Homo sapiens fossils in Ethiopia. So that's one of the things.
Wow. So what age have we pushed it back to?
So it's about 225,000 years.
Wow. Wow. Zach asks, are ice cores becoming less reliable due to climate change, with obviously with the retreat of the ice caps?
I don't think they're becoming less reliable, certainly not in the poles. If anything, the information they have is of even greater importance, because we know that the Arctic area and Arctic and Antarctic are such fragile and sensitive areas that the more we can find out, the better from these ice cores. Where it is having an impact is in low latitude ice cores. So our longest ice core records come from the poles on the big ice sheets in Antarctica and in Greenland, but there are also some really wonderful shorter ice core records from mountain glaciers around the world. And of course, those are receding much faster. They're smaller and they're at lower latitudes. And we're going to lose the option of drilling and studying those, I guess, before our polar ice cores become problematic.
Madeline asks, how far back do Tephra chronology records go?
Wow, well, people have been using Tephra chronology almost throughout geological time, I guess. Although we're not able to pick apart the sediment and find tiny layers when things are lithified into rock. So I guess most of the work then that's done in the way that we're doing it is from the Quaternary, or maybe into the Pliocene, which is the period before the Quaternary. So 2 to 3 million years, I guess.
It's amazing. It's just amazing, isn't it? When you think about it, that is amazing. Jack asks, which lakes obtain the most diverse tephra cores or layers, I guess?
Oh, from the most places, let's think. I don't know the definitive answer to that, but if I think about a place that's got, I did a study a few years back in Lake Bled in Slovenia. I don't know if anyone's ever been to Slovenia, but there's a beautiful alpine lake in Slovenia, and the record in there was really interesting because it captured Icelandic and Italian volcanism for the first time in the same record, which we hadn't found until then. So we had, and the interesting thing was we discovered that there were two tephra layer from Iceland, so actually the Vedda ash we've been talking about. The age of it is about 12,120 years, plus or minus 100 years, right? That's the precision we get from the ice core. So we've got about 200-year uncertainty on its absolute age. There's another eruption from Italy, dates also to 12,100 years, and again had about 200-year uncertainty on its age. So we didn't actually know the sequence that they occurred in. So by finding them in this lake core, we found out that the Italian layer, I think I'll get this the right way around. No, the Italian layer was 1 centimeter above the Icelandic layer, the Vedda ash. So by finding tephra layers from different regions, we can start to sort of intermesh and refine the dating of different layers. So we could say, well, we know that this one must be, wherever we find the Vedda ash, we now must be older than the Comitia Principale layer. So it's quite interesting when we start to overlap them. There are sites in Europe that have tephra from lots of different sites. I guess even that Meerfelder Lake has Italian, French, Icelandic tephra layers in it, I think. Possibly something from the Azores.
So I'm conscious of your time, Christine. You've given us a lot already today, but Reese would like to know, I don't know if he's being flippant, but what do you do with your research?
Well, I mean, the idea is that we publish it. So we publish lots of work in scientific journals. But I also try to think, more recently, I've been thinking about, what are the kind of real world applications. So my work is part of typically I work on these collaborative projects where I'm working on the dating. Other people might be doing the paleoclimatic reconstructions from diatoms. Somebody else might be working on pollen. Somebody else might be working on the sediments. And we all come together to try to understand what's been happening at a site. And then we have to work out, who cares? What are we trying to find out? So you look for the bit of the story that's useful for understanding the climate system. So my little bit is part of a bigger study, I guess, most of the time. And then our data is made available, I guess, to people who are interested in, or people who are doing climate modeling, who might be trying to reconstruct. Can they test their models and find out what we found out? Do their models show the same thing if they run them over the time period we're working at? So some of the networks I work within, those are the kind of interactions that are happening. We're making climate reconstructions and other people are testing their models against them. But the actual model testing bit isn't my expertise at all.
And then I think conscious of time, so just one more. I've had quite a few questions about this across the day, but as a student at Cambridge, if you discover this little interesting sort of research that's going on, how do you get involved with it?
Yeah, it's always one of those things that you kind of arrive in and you don't know how to find out about it or get involved. So I always encourage my students to talk to people as much as they can, to attend seminars whenever they can that aren't the kind of lectures, but when you get an opportunity to hear about something that someone's doing, when you get the opportunity to see an external speaker come in, you can discover these things that you didn't know about or that might not be core to the curriculum. And then the opportunities you get here, you get lots of chances to talk to people, lots of chances to interact with the academics and say, hey, can I come and see your lab? Or can I come and talk to you about your work? Or have you got a PhD student I could help if I would like to find out what it is they do? And I quite often have students who are interested in doing certain types of lab work, might come and shadow somebody for a day just to see if it's something that they would like to do for their dissertation later on. We have field trips and there's lots of opportunities to talk. And I think it's different for different academics, but I'm always keen to give people an opportunity to try something, even if some people don't like lab work, some people love it, but until you've tried it, you don't know. So there are lots of opportunities, I think, if you talk to the academics here, to help out with something or to get involved prior to the kind of dissertation formation. But in the end, the dissertations that you do, the research dissertations our students do, are really where they get stuck in on a research project of their own. And often those research projects are run in parallel to something that an academic is doing. So it might be working as part of a research group.
Yeah, I think as well to emphasize, the benefit of going to somewhere like Cambridge is the amount of contacts you get with your academics, across all 3 years. And, I stressed it a little bit in my admissions talk, but, if you are motivated, you show some initiative and independence, essentially, if you ask for things, you ask for opportunities, you're coming to the right place where there are lots of those things available. You just have to show a little bit of gumption and just ask for things. Ultimately, isn't like everyone's here. Everyone, there's a lot of people here who will help you and direct you to things, but we don't know to do that unless you ask us for a little bit of help, if that makes sense. We've had you for an hour now, so I mean, there's still some unanswered questions, but I think, in interest of, you're a busy person, and I'll say on behalf of everyone, thank you very much for your talk.
You're very welcome.
Yeah, and answering all the questions.